Can you see it?
Yes, sure. Can you make it full screen?
Yes.
Okay.
All right. Does that work?
Yeah, it's perfect. So now we have Olaf Hohm with a talk on duality and high derivatives. So 30 minutes, please.
Okay, thank you very much. So let me also thank the organizers for setting up this wonderful conference and for giving me the opportunity to talk here. So I'm very excited about this because my own research fits very well, I think. So I will tell you about duality and higher derivatives. So this is the higher derivative alpha prime corrections in the context of string theory. And I will be mainly concerned really with classical string theory. So one of the interesting features of string theory is that already classically it modifies Einstein's theory of general relativity by an infinite number of higher derivatives. And it's just interesting to try to understand how this classical theory looks like. So I will talk mainly about work I've done in the last 2 years or so with a number of people, including Barton Zwiebach, Camille Eloy, Henning Samtleben, Roberto Bonezzi, Felipe Diaz, Thomas Codina, and Diego Marquez. And this is sort of focusing on a traditional or sort of old-fashioned approach to look at duality and T-duality in string theory. But this goes back to sort of a larger research program that goes under the name of double field theory, where there are some hints or some promises that the alpha prime corrections might be encoded in some exact form in a novel kind of geometry. So this goes back to papers by Siegel and Zwiebach, and then some follow-up work. But for the purpose of this talk, I will not mention double field theory further. So this I will focus on this sort of traditional approach, which people would have understood in the late 80s or early 90s. Okay, so okay, now I don't know how to change my page. Here we go. So here's the plan of my talk. So I start with a one-page review of T-duality and higher derivative alpha prime corrections. So for the non-string theorists to set up the language. And then I have three main topics. The first one is a complete classification of alpha prime corrections for cosmological backgrounds. So basically I restrict myself here to very special geometries which depend only on one parameter, which you can think of as time. And in that case, of course, which is very special, one can use the duality property to give a very simple characterization of all possible higher derivative corrections that could be there. In the second part, I will generalize the discussion to a generic compactification, so not just to one dimension, but to an arbitrary number of dimensions. And here we have to restrict to first order and alpha prime. But in this more general setting already to first order and alpha prime, there's some novel phenomenon that was not noticed earlier, namely that the ODDR transformation, so this group ODDR is the group related to T-duality that controls everything I'm saying here, that those transformations get alpha prime deformed in the form of a generalized Green-Schwarz mechanism. And then the final and the third part of my talk, I will discuss this phenomenon from the point of view of a worldsheet derivation. Namely, there's a duality invariant worldsheet one can write, and it turns out that this has certain anomalies that give a worldsheet interpretation for these alpha prime deformed transformations. Okay, so let me begin by reviewing T-duality. So T-duality traditionally arises when you consider string theory on a toroidal background TD. So you have a d-dimensional torus, and let's assume that I have a constant background metric and a constant B field on this torus. And I combine the metric and B field into a general matrix E. And then the statement of T-duality is that if I change the background, so if I go from E to a new background E prime, by this formula here, so this is a particular fractional linear transformation with a matrix A, B, C, D, that lives in the, so this is a 2D by 2D matrix where A, B, and C, D are D by D matrices that lives in the group OD, D. So if you do this transformation, you map a background to a new background that, however, gives rise to an equivalent string theory. So for instance, one can discuss that in the context of string field theory, as done by Kubo and Zwiebach, but of course that has also been discussed in numerous alternative contexts. Now, one feature of this T-duality is that it maps Kaluza-Klein modes into winding modes. So if you have a theory defined on a torus, you can of course do a Fourier expansion, and then the higher Fourier modes of the conventional fields are Kaluza-Klein modes. But in string theory, there are further states, which are the so-called winding modes, and they are mapped into each other. And because you're on a torus, and so there are periodicity conditions, the duality group is really O d, dz. So you're considering matrices with integer entries. Now, while this is true, once you truncate to the massless fields, in other words, you throw away the Kaluza-Klein modes and the winding modes, the higher ones, you keep only the zero modes. The symmetry is enhanced to O d, dr. So you have a continuous symmetry. And that's simply due to the fact that you've lost essentially all memory of the torus topology. So it makes sense that then you have an O d, dr symmetry. And this is important because it tells us that as long as you have sort of d directions on which the fields do not depend, so you have a d-dimensional translation invariance, there's an O d, dr symmetry in string theory, no matter whether the dimensions you think of as compact or non-compact. And in fact, this is a general result due to Ashok, that classical string theory with d-dimensional translation invariance features a global ODDR symmetry to all orders in alpha prime. So this gives us control over the alpha prime corrections, and this is what I will use in the following. Are there any questions on this first slide? Well, sorry, we don't do questions right now, right? So I guess I can just keep going. So let me start with the first part, the cosmological setting. So let's consider target space string theory. So we have massless fields, let's say in 10 dimensions or 26 dimensions if you do bosonic string theory. And universally, these include the metric G mu nu, and then antisymmetric tensor B mu nu, and a scalar field, which is called the dilaton. And we can write down a space-time action for these fields, which is written here. So you have the familiar Einstein-Hilbert term here in a particular form with a dilaton prefactor. So this is the so-called string frame. And then there's a kinetic term for the dilaton and a kinetic term for the B field. So this H, here's the 3-form field strength for the 2-form B. And that's, of course, the familiar action you can write. But it's also just the first term in an infinite number of higher derivative alpha prime corrections. Now, in order to see duality in the simplest setting, T-duality, you can perform a dimensional reduction to, let's say, one dimension. You can think of this one dimension left as time, or cosmic time, if you think of cosmology. And so we make the following ansatz for the metric, G mu nu, for the B field and the dilaton. So here we have just an internal purely time-dependent metric, purely time-dependent B field, and a purely time-dependent dilaton. And this n of t is just a lapse function. It's a 0, 0 component of the metric, which you could gauge to 1. If you plug this into the action, of course, it simplifies dramatically because all derivatives reduce to time derivatives. And so you get an action of this form here. You have a dot as the time derivative. You have a phi dot squared term. You have a combination of g dot squared and b dot squared. And this capital phi here is a particular redefinition of the original phi using the determinant of the internal metric. And it just turns out that this is a convenient variable in order to see this duality symmetry. Now, if you just look at this action, this is just, of course, of the generic form you would expect for a theory reduced to one dimension. You just have a first order time derivative squared of some fields. So nothing too special here, apparently. But it turns out that this has a larger symmetry than a generic theory of gravity coupled to some generic matter would have in one dimension. And this is this ODD symmetry, which is a hidden symmetry in the original formulation, but it can now be realized as follows. So in order to see the symmetry, we reorganize the fields into a 2D by 2D matrix, where the small d here is the number of spatial dimensions, so it's capital D minus 1. And we take the internal metric G and the internal B field B, and you organize it into this nonlinear form. So this is a 2D by 2D matrix. So this capital indices Mn run from 1 to 2D. And this particular nonlinear form of the matrix is fixed by the requirement, or it obeys the requirement that this is an ODD matrix. Or in fact, we should think of this as coming from an ODD coset model. And one way to state the constraint is to say that suppose I raise the index of H to define a matrix S using the ODD invariant metric to raise the index. So ODD is the group that leaves a metric of signature D, D invariant, and we choose this particular off-diagonal form. So if I use this metric to raise the index, this matrix can be naturally squared. So it has a structural form of a linear map. And the square is just identically 1. So in that sense, this is a constrained field. You can check that this matrix satisfies this constraint. And now the point is that this action I just showed you can be reorganized, can be rewritten just directly in terms of this matrix S, H or S. And these terms we just saw here, they are just S dot squared terms, as was first shown by Meissner and Veneziano, the early 90s. And so that immediately tells you that this action has an ODD invariance. So you can transform S to S prime by an ODD matrix H, and you can just say phi is an invariant, which is the reason that this was a good definition. And since S itself is an ODD matrix, this is of course a well-defined transformation. So it tells you that this action has a global ODDR invariance. And this is exactly what we would expect from string theory. So this works very nicely. You can realize the symmetry explicitly to lowest order in alpha prime, and you just get this S dot square term. It's just neatly written in terms of this ODD matrix. So let's now include the alpha prime corrections. And this was first done in a very impressive paper by Christoph Meissner, I think in 96 or 97, to first order an alpha prime. And so it becomes a very tedious computation. And it turns out that in order to have any chance to push this to higher order in alpha prime, one really needs to have full control over all possible field redefinitions one can do. And this is a result of a classification I did with Zwiebach a few years ago. Again, in this cosmological setting where everything depends only on one dimension, time. And the result is the following. If you just ask, what is the most general action I can write that is ODD invariant, so that uses this matrix S, this ODD matrix, but I allow myself to exploit all possible field redefinitions. So in string theory, these particular terms that may arise in higher order are anyhow only well-defined up to field redefinitions. And using this, we found a very simple structural form for the higher derivative terms. So here are the first couple of terms you could have. So the general pattern is, the general result of this classification is that you have only first order time derivatives. So a priori, I could, of course, imagine all kinds of higher derivatives here, but I only have higher powers of first order time derivatives. Only even powers of S enter. That just follows from the group property, in fact. I have no higher derivatives of phi itself. So phi appears in the lowest order term with phi dot squared, but there are no higher order terms. And I also need no trace S dot squared terms. So that means that to first order an alpha prime, in fact, there's only one term I need to write. So there's only one coefficient that is not already fixed by duality. Then at second order an alpha prime, there's still only one coefficient. And only at the third order in alpha prime do I see the second invariant arising, which is this one here. So in fact, you can just count the number of free parameters that you have at any given order alpha prime to the k, and it's given here, where p of k is the number of partitions of an integer k. Of course, this number is growing, but it's growing sort of much more slowly, I think, than a naive sort of attempt to classify those terms would have shown. Now, all these coefficients, of course, are not completely known. In fact, the very first one for bosonic string theory was worked out by Meissner in that paper I mentioned. And now if you look at type 2 string theory, for instance, that was only established very recently in a paper with Thomas Codina and Diego Marquez. So the first two coefficients here are in fact 0. The alpha prime corrections for type 2 start at order alpha prime cube. And there at order alpha prime cubed, you get this famous zeta of 3 coefficient appearing. In fact, in the first version of this paper, we got this wrong. We seemed to find an obstacle for ODD, but that was just a technical mistake. Once you fix that, it works beautifully. But of course, this is just to third order and alpha prime, and remains an infinite number of free coefficients to be fixed. Now, you may wonder what's the use of this if you don't know those coefficients. Well, you can just play with it a little for fun by working out how the Friedmann equations are modified. So if you want to do cosmology, that's of course the natural thing to do. So we could use an FRW ansatz where the metric is just a scale factor times the constant metric. And let's say we set the B field to 0. Then you can write the Friedmann equations in a closed form by defining a single function of the Hubble parameter h. So the Hubble parameter is here, a dot over a. And this function is defined as a power series in h in terms of those coefficients ck, slightly redefined here, that were given in this general classification. Of course, we don't know what these coefficients are, but if I knew them, I could define this power series. And then I would know everything about the Friedmann equations, which are given here. So here, this function small f and small g are just defined in terms of this capital F, where the prime is the derivative with respect to the Hubble parameter. And now here are the Friedmann equations. So there's one equation that tells you that this combination here is constant in time. In fact, you can think of this equation as coming from the Noether theorem due to the ODD symmetry. Then there's an equation for the dilaton, and then there's an equation for the lapse function, or for the 0,0 component of the metric, aka the Hamiltonian constraint. So here are the equations. Those should be the complete equations to all order and alpha prime. Of course, again, we don't know those coefficients, but you can play with it. For instance, you could ask whether there could be theories, meaning coefficients with a corresponding function f of h, so that the Hubble parameter, E being equal a constant, a non-vanishing constant, is an exact solution. That would be interesting because that would precisely be a de Sitter solution. And in fact, it's easy to write such functions that have this property. So if it would happen that string theory gives rise to a function of this form with this property, then one could say that they are non-perturbative de Sitter solutions. Non-perturbative in alpha prime, because to lowest order in alpha prime, of course, there is no de Sitter solution of these equations. But of course, as I said, this is at this point just playing with these numbers, trying to see if one can fix them in a convenient way. Eventually, string theory should fix them uniquely. Okay, so that was the cosmological part. Now let me come to the second part, which is general compactification. So on more general tori. So here, I want to consider now a compactification of this kind, where I split the coordinates x mu hat, so these are the full coordinates in 10 dimensions, let's say, into a number of arbitrary external coordinates x mu, running from 1 to capital D, and then a number of internal coordinates ym, running from 1 to small d. And we do again a dimensional reduction, meaning I assume that the fields do not depend on the yms. Now, the analysis, of course, is much more involved technically. And on a conceptual level, the interesting new thing happening compared to the cosmological setup is that now the B field enters in a more important way, meaning that I've now an extra vector components coming from the off-diagonal part of the B field, and I have also an external B field, so a B field in the external number of dimensions. So this did not survive in one dimension, of course, because there's no two form in one dimension, but it does show up in general, and I emphasize this now because this will play a crucial role in a minute. Now, this extra vector combines with the vector from the metric, the so-called Kaluza-Klein vector, into an ODDR vector. So I need two vectors to make an ODD multiplet, and this is given here. And it turns out that this ODD vector nicely combines with the field strength of the B field to give an invariant field strength that has this Schoen-Simons or Green-Schwarz time modification. And if you do this compactification, you can write down a manifestly ODD invariant action, which was worked out in this very nice classic paper by Maharana and Schwartz from '93. And here it is. So everything is ODD invariant. You have, again, kinetic terms for this ODD matrix. So the form of this ODD matrix is exactly as before. Then there's coupling to the gauge vectors. So there's a Yang-Mills term here, and then there's some external pieces that we also didn't see in one dimension. Okay, so that's all to zeroth order in alpha prime. Let's now go to first order in alpha prime, and that's a very recent result. Well, a little more than 1 year ago. That if we now include the first alpha prime correction, let's say as given by Metsaev and Zeitlin in '87, and do a compactification, do I still get an ODD? And again, one has to develop a rather sophisticated technology to deal with all possible field redefinitions to have any chance to see this ODD symmetry. But this can be done. And doing this compactification, we do find a nice ODD invariant action, which I call I1 here, plus some extra terms that are kind of funny. And so the first part looks sort of more or less as you would expect. There are a bunch of higher derivative terms. There are higher derivative terms involving this matrix S that I showed you earlier. And in fact, there's a series of terms here, 30 more terms I wrote out. So the whole action is like half a page. Not the simplest thing ever, but compared to some of the intermediate results you get, it's a quite drastic simplification and a very neat result. So that part works exactly as one would expect. But then there's those extra terms O1, which are of this structural form here. They couple the normal abelian field strength of the B field to some three-form omega, which is of third order in derivatives. So the whole thing has 4 derivatives. And involves particular combination of the internal metric and the internal B field as written here. So at first sight, you would try to rewrite this again with this ODD matrix S, but you can quickly convince yourselves that that is not possible. In fact, this object here, this three-form, does not transform as a scalar under ODD transformations. So rather what's happening is the following. That there's a generalized Green-Schwarz mechanism happening. So this omega-3, this three-form cannot be written in terms of an ODD matrix, but its exterior derivative can. So there's some kind of homological approach you have to choose here. So the exterior derivative omega-3 has this nice expression in terms of the ODD matrix. So it's a 4-form as written here. And of course, this is manifestly ODD invariant. So it's a singlet because there's a trace. Now, this tells you that this 3-form omega-3 must transform into something exact so that both sides of this equation here are invariant. And in fact, one can check this using the explicit expression here. So I can work out what this 2-form X2 is. Now, this means that I can fix the ODD invariance that seems naively broken due to those extra terms here. I can fix this by defining the alpha prime corrected curvature given here, where I shift the normal 3-form by minus alpha prime omega-3, because the transformation of omega-3 coming with dx2 can then be cancelled by assigning the following transformation to the B field, B2. So I just tell you that has this transformation with alpha prime x2. X2 was this two form defined here. And then, of course, they just cancel. So this is a non-standard or Green-Schwarz-like because the two form I'm using here is an ODD singlet. So in the two derivative theory of Maharana and Schwarz, this, of course, didn't transform under ODD. But it turns out that to higher order in alpha prime, it does receive a non-trivial ODD transformation. And in fact, this is exactly analogous to the standard Green-Schwarz mechanism, if you're familiar with it. And in fact, the analogy can be made more precise by noting that if you go to a frame formulation, so if you don't work with a generalized metric, but rather you introduce a frame field for this object, you can define composite SOD cross SOD gauge fields. So SOD cross SOD is the group of frame transformations in such a formulation. And with these composite SOD cross SOD gauge fields, so Q call the composite gauge field for SOD left, let's say, and Q bar for SOD right, one can in fact show that this omega-3 is the difference of these Schoen-Simons three forms. So that's now exactly of the form of a standard Green-Schwarz mechanism, except that here the gauge fields are composite. Okay, so that was the second part of my talk, realizing the ODD in the general compactification of first order and alpha prime. And now I will close the last 5 minutes by discussing the third part, how to understand this from the point of view of a duality invariant worldsheet. So I want to write now a worldsheet action that is sort of adapted to this framework of dimensional reduction. So I want to write a worldsheet action that has target space fields that are independent of d coordinates ym. So I can do this, for instance, by writing just a standard worldsheet action that I would write on a torus, for instance. But then I make an additional truncation where I truncate the Kaluza-Klein and winding modes, as I mentioned earlier. And then one can, in fact, prove that this resulting worldsheet theory can be rewritten or is on-shell equivalent to one that is manifestly ODD invariant. So this is goes also back to the early 90s due to work by Zeitlin and then later by Schwarz and Sen. So you have an action of this structural form here. So this is just looks like a normal sigma model coupled to a B field, but then there's some extra terms which are ODD invariant, which couple to the ODD invariant Kaluza-Klein vector. And here the x mu are the internal scalars. Sorry, the external scalars, the ym are the internal ones, and they are doubled. So note here that this ym has 2D components. And these functions u and e is just particular components of the worldsheet metric h alpha beta. So here you see already that the two-dimensional diffeomorphism invariance is no longer manifest, but it's still there. It's just not manifest. Here we have a covariant derivative. And now one of the points is that if you go on shell, if you work out the equations of motion for y, you can in fact integrate them and use some of the gauge symmetries to show that they are equivalent to these duality relations. So these are first order differential equations, and these sort of explain why you got away with doubling these coordinates. So if you think of a normal worldsheet, you have just d coordinates. Here we have doubled them, but at the same time, there are duality relations, which really tells you that only half of them are still there. So you can think of this, in fact, as telling you that they are chiral bosons. So that if you take a particular split of this 2D index into d-dimensional indices, you can show that they are killed by half of the derivatives if you use this light cone basis here. And in fact, that kind of reasoning is behind showing that this is equivalent to the standard on-shell equivalent to the appropriate worldsheet action. So because there are chiral bosons in the game, one should, of course, suspect that there are anomalies, and indeed they are. So if you take the worldsheet action, which is SOD cross SOD invariant, which is the invariance group of the generalized metric HMN, or this ODD matrix here, you can write down conserved currents corresponding to this SOD cross SOD. But on shell, half of them are 0. And that's just, again, the statement that on shell, those derivatives here are 0. So the conservation law classically has this form for the surviving currents, where it's only one term and the other one is 0 because the current is 0. So that tells you that if you look at the naive Ward identity that you would need to have naively to this conservation law, that one of these terms is actually 0 because it contains a J minus here, which is 0 on shell. So you can kill it. So if only the first term left, and so this by itself must be 0. And so this implies that this 2-point function should be 0. But in fact, we know this 2-point function cannot be 0 as the 2-point function of anti-Hermitian operators. And in fact, you can also compute it explicitly, and it's just not 0. So this tells you that this Ward identity is violated. And so there's this SOD cross SOD is anomalous. And in fact, you can work out the one-loop effective action defined here, where you integrate out the y's, the internal scalars. And one can check that this transforms to lowest order in a SOD cross SOD in a non-trivial way. So it's not an invariance, but of course the structure is exactly as you would expect, or as you would like it to be, in order to be able to cancel it by assigning an appropriate transformation to the B field. So that's exactly the Green-Schwarz mechanism. And if you go back here, the B field has this coupling, which is important to include if you go if you want to make a quantum mechanical treatment of this action, because if you include it, you can cancel the anomaly by just assigning this classical transformation to the B field. And that's, of course, exactly what we saw from the target space analysis has to be done in order to realize ODD. So in this way, we have obtained a worldsheet interpretation of the target space Green-Schwarz deformation. And this story is again exactly analogous to what people did for the heterotic string. So was shown by Hull and Witten and Sen that that you can give a similar a worldsheet interpretation for the standard Green-Schwarz mechanism, and it works in the same way. Okay, so I'm basically done. Let me just summarize and give a brief outlook. So I told you how the duality invariance allows one to completely classify alpha prime corrections in the cosmological setting, I should emphasize here. So one intriguing possibility is to possibly have a test of string cosmology scenarios. So there actually were a number of papers exploring this, and I guess some of the people are maybe in the audience, so we can perhaps discuss this further. So unfortunately, I didn't have time here to collect the references, but this is something we may want to discuss. I showed you also that going beyond the cosmological setting, so to a general compactification, duality invariance requires that the transformation are alpha prime deformed, giving rise to a generalized Green-Schwarz mechanism. And this also had a worldsheet interpretation. So something we're doing right now is to try to use this worldsheet, this duality covariant worldsheet, to compute beta functions and establish a vanishing of the Weyl anomaly in order to derive target space equations that are immediately duality invariant. So this will give us the Majorana-Schwarz action plus alpha prime corrections. And then there are various possible generalizations, let's say to U-duality, or to various versions of a full-fledged double field theory, which is sort of the larger goal in this research program. So let me stop here. Thank you very much.
Okay, thank you all very much for a nice talk. So there are some questions, and the first appeared from Ivano. Basil, can you unmute yourself and ask?
Hi. Hi, can you hear me?
Yes.
Yes.
Okay. Hi, thanks for the very nice talk. This is very interesting. And so I have a couple of questions, if I can. So first is more conceptual, namely, I was wondering, what would you think is the most promising approach to compute in the cosmological scenario where you classified all the corrections? Well, all of them. Like, how would you go about investigating these all of their coefficients?
Well, I mean, that's what I'm trying to figure out now. So the obvious approach is what I wrote here, is to sort of follow the textbook approach, compute beta functions, and demand that the worldsheet theory is conformally invariant quantum mechanically, and that gives you constraint on those coefficients, or will determine them in principle. Now, this is obviously still very messy, even in the simplified setting. So the alternative would, of course, be to try to compute string scattering amplitudes and try to infer from that the coefficients of the corresponding terms in the action. In which case, one has to think, of course, what you can do when only the time coordinate is left. So I don't really have any novel approach to offer here to determine those coefficients. I think these are the obvious methods.
Right.
Yeah.
Right. I mean, maybe I suppose that, as far as the worldsheet beta functions go, if you already restrict the sigma model on the cosmological background with the whole duality invariant formulation, maybe some all-order results could be somehow feasible, but I wouldn't know about that. But my other question is very specific instead. It's about the cosmological equations, right, for de Sitter solutions especially.
Yeah.
And there's something that I think you didn't mention, but so as far as I gathered from your papers, you said, like, it's written there, I think, that for de Sitter solutions, the dilaton has to be constant, and somehow it follows from the first equation, right? But then, since it also implies that little f needs to vanish, I mean, it doesn't seem to necessarily imply that the dilaton is constant, because if you put little f to 0, in principle,
yes.
the first
So
equation is already...
Yeah, so there was actually a paper fairly recently by Carmen Nunez and collaborator. I don't know if you... Sorry, who are you again? Who's asking?
It's
are
me.
You an author of that paper, or
No, I'm not.
Okay, so if you don't know that paper, there's one. So there's yeah, I think we say something in the paper that is not, the way it's written is not correct. So we assume that the dilaton is constant, in which, when we construct a string frame de Sitter vacuum, well, right, we don't construct one. We give a function f of h, so that there are a string frame de Sitter vacua, but this assumption is not needed, and they showed that then you can also get Einstein frame de Sitter vacua.
In general, like from the second equation, you get basically that it can be a linear profile. See, yeah, so that was my question. Thanks.
Okay.
Okay, one more question here by Anupam. Anupam, where are you?
Hi, Olaf. Thanks a lot for this lovely talk, and it has caused quite a lot of interest in the cosmology community. So one question we were discussing actually today while you talk, that why would you expect the cosmological perturbations to preserve the OD, D symmetry? I would not expect the cosmological perturbation will preserve it. And so then you're back to your old problem. You have to face all the infinite derivatives.
Around you, or which perturbations you have in mind?
So the cosmological perturbations.
I think my internet connection is unstable. Can you hear me?
Yeah, yes, we hear you.
Hello?
Yes, we perfectly hear you.
Okay. Yeah, so you asking about the cosmological perturbations, and in this case, generically the ODD is broken unless you assume that dimension to dimension toroidal, and then you can restore the ODDZ by including the winding Akusa-Klein modes. So this is in fact something a student of mine is working on right now. But you're right, in general, the ODDR is certainly not there anymore.
So then would you expect that, again, you will have to face the entire, infinite derivative equations of motion instead of two derivatives?
Well, it depends what you want to do. I mean, here is the question was, can you, what are the cosmological solutions you can have? Now, if you want to do cosmological perturbation theory, let's say compute 2-point or 3-point functions, then of course you have to redo the analysis. So now for the 2-point functions, for instance, you only need the quadratic action, I guess, and as Ashok was reviewing, at least for flat space, there you don't have any higher derivatives. So depending on what you have in mind, you could still go, I mean, you may not need to include infinitely many derivatives for your computation. But of course, as a point of principle, you're right that then you have to include them.
Yeah. So
I haven't
Shravan,
really
what
thought
your
about the
question?
cubics.
Hi, so thanks for the talk. I have a confusion between string theory and string field theory. String field theory talk we heard from Ashok, where non-localities are naturally emerge. Now your action, you say it is string theory. I mean, is it computed from string field theory? Then where are the non-localities? If it is not from string field theory, then from where this action comes from?
So this action, do you mean this action here, I suppose?
Mm-hmm. Yeah.
Yeah. So, well, the two derivative part comes just from the familiar low energy action that we have here. So that's the known two derivative contribution, which you can also get from string field theory restricting to two derivatives. And these higher order terms are not computed from string field theory. They're computed, in fact, you could say they're not really computed because I don't give you those coefficients, but they are constrained by exploiting this ODD-R symmetry that by this general argument due to Ashok is known to exist. So, and then we prove in this paper that these are the independent terms you have to include. So any other terms at any given order in alpha prime, you can remove by appropriate field redefinitions.
So then I'm again confused. Why, from where this symmetry emerges? I mean, from any principle? So
yes. So so this was this general. Well, I don't give an argument here. So that's a simple argument due to Ashok. If he's still around, he may want to correct me if I say something wrong. But you basically use that at tree level, there's an OD left times OD right symmetry manifest in string theory. And then you use this OD left times OD right symmetry. So this is all for the truncated sector, I should say, where you use the d-dimensional translation invariance. So you assume that along d directions, there's no dependence. And so then you have this OD left times OD right. And you also know that there are, of course, diffeomorphisms and B-field gauge transformations, which give rise to global transformations if you just take the parameters to be linear in coordinates. And if you combine all those symmetries, you can prove essentially by counting the number of generators that there must be the full ODD-R. So that essentially is the proof. So there must be this ODD-R symmetry for classical string theory's d-dimensional translation invariance, and cosmology falls into this framework. If the spatial metric is flat. If the spatial metric is flat, you can just take the fields to be independent of the corresponding coordinates. This, of course, does not work if you have a non-flat cosmology. So this is for cosmologies with flat spatial metric, but this works to all orders in alpha prime. So using this, we proved that this is the action given here.
Okay, so I suggest that we thank Olaf again for his nice talk, and